So we pick up with the diode characteristics. So we've learned a little bit about the physics of what's going on between electrons and holes and the characteristics of the P and the N materials, trivalence, pentavalence, things of this nature. So let's see how this comes together in a discussion about the diode and what goes on electronically in a circuit. So as we saw in the last section, a diode is a semiconductor device made with a single PN junction. A diode conducts current when it's forward biased, when the bias voltage exceeds the barrier potential. A diode prevents current when it is reverse biased at a less than breakdown voltage. So we can start thinking about a diode as having switch characteristics, which only allow current to flow in one direction, unless we max it out reversed, and we'll learn a little more about that when we get into the characteristics and further on with the Zener diode. So if we take a look here, the diode characteristic curve, this is something that you need to ingrain in your mind whenever you see or think about a diode, because it is the characteristic. So we can see on the right half of the screen here, or the right half of the graph, where we have the I forward, I reverse, V forward, V reverse, where we have the forward bias. This right down here is what's called the knee of the curve, and you can see what happens here is that as the bias voltage is increased until it reaches 7/10 of a volt, then it spikes up and the current begins to flow. So the upper right quadrant of the graph represents the forward bias condition. As you can see, there's very little forward current for forward voltages below the barrier potential. So down here in this region, flat on the V sub F axis. As the forward voltage approaches the value of the barrier potential, the current then begins to increase. So you can see right here, it's starting to try to come up until it reaches this point right here at 7/10, and then it takes off. Once the forward voltage reaches the barrier potential, the current increases drastically and must be limited then by a series resistor. And we saw that in the previous one, where we had a little load resistor in line there. The voltage across the forward bias diode then remains approximately equal to the barrier potential. Again, 7/10 for silicone. Okay. So the lower left quadrant of the graph represents the reverse bias condition. Okay, so we can see it looks almost the same here, but the current is going negative. As the reverse voltage increases to the left, the current remains near zero until the breakdown voltage. Okay, and we show that as V breakdown. When breakdown occurs, there's a large reverse current, which, if not limited, can destroy the diode. Typically, the breakdown voltage is greater than 50 volts for most rectifier diodes. Remember that most diodes should not be operated in the reverse breakdown mode. Okay, so there's your graph. There are actually test equipment. I don't know if in your lab they will have you use it for this course, but there is actually a piece of test equipment excuse me, that plots this out for you. So we look at what goes on symbolically with a diode. We can see here we've got a diode symbol here. It looks like a little point with a line on it here, and we can see what's going on in terms of current flow when we diagrammatically show a diode as a schematic symbol. The basic diode structure and the standard schematic symbol for a general purpose diode, the arrowhead of the symbol points to in the direction opposite the flow of electron current. The two terminals of the diode are the anode and the cathode. I know it's with a C, but they show it as a K. The anode is the P region, the cathode is the N region. When the anode is positive with respect to the cathode, the diode is forward biased, and the current I forward, I sub F, is from cathode to anode. Remember that when the diode is forward biased, the barrier potential V sub B always appears between the anode and the cathode. When the anode is negative with respect to the cathode, the diode is reverse biased and there's no current until you force it. A resistor is not necessary in reverse bias, but is shown for consistency. Okay, so they show it there for you. So if you take a look at the diagrams here, it gives you an idea schematically what goes on in a simple circuit with a diode and a source providing the bias voltage. This is just a depiction of what a diode may look like. Typically in the lab, you're going to use the diode configuration that looks something like this one up here, where it says AK. These others are available, but in the lab condition, they're not going to be as numerous for you. Diode approximations. We start with an ideal diode and ideally model it. The simplest way to visualize diode operations is to think of it as a switch. When forward bias, the diode ideally acts as a closed on switch, and when in reverse bias, it acts as an open off switch. The VI characteristic curve for this model is shown below, so you can see the simplistic model without the knee and without the eccentricities of current going off at kind of at an angle. Okay, note that the forward voltage V sub F and the reverse current V sub R are always zero in the ideal case. So if you step through the diagrams here, you can see for the forward bias condition, we forward bias, the diode goes into conduction, and we have current flow, negative to positive. In the reverse bias, you can see it's indicating it as an ideal model, no current flow at all. The ideal model then, of course, neglects the effect of the barrier potential, the internal resistances, and other parameters. You may want to use the ideal model when you are troubleshooting or trying to figure out the operation of a circuit and are not concerned with the more exact voltages or of voltage and current, the values of voltage and current. So next we have the practical model. The next higher level of accuracy includes the barrier potential of the model. In this approximation, the forward bias diode is represented as a closed switch in series with a small battery equal to the barrier potential, so 7/10 for silicone. The positive end of the battery is toward the anode. Keep in mind that the barrier potential only has the effect of a battery when forward bias is applied because of the forward bias voltage V bias, and it must overcome the barrier potential before the diode begins to conduct. The reverse bias diode is represented by an open switch as in the ideal case. Because the barrier potential does not affect reverse bias, the VI characteristic curve of this model is shown. So again, if we take a look at the model, you can see here that characteristic just like the ideal case, and again no reverse bias in the left hand quadrant of the graph, but you can see ideally modeled it goes from 0 to 7/10 and then the current begins to flow considerably. In looking at the complete diode model, one or more level of accuracy will be considered at this point. The diagram shows the forward biased diode model with both the barrier potential and the low forward dynamic resistance. So you can see here in the diagram here of the graph what's going on, and if you match it with with this little schematic diagram here where we have some internal resistance in series, some internal resistance in parallel. The figure shows how the high internal reverse resistance affects the reverse bias model. So you can see we're developing that curve with each step as we move from the ideal to the more practical model for the diode. Okay, other parameters such as the depletion region capacitance and breakdown voltage become important only under certain operating conditions, and it will be considered only when appropriate. So when we come back, the next thing we will take a look at are diode diode rectifiers. And the diode rectifier then is what we're going to do to start putting the diode to work as components for power supplies.